a mesmerizing cosmic tapestry of stars, galaxies, and nebulae woven together by the threads of the universe itself. But what happens when we find a breach in this grand design? A place where the cosmic loom seems to have jerked, leaving an almost unfathomable immensity. Nothing. Imagine an area of space so vast and empty that if you traveled at the speed of light, it would take you more than 330 million years to traverse it. That's about 23 times larger than our own Milky Way galaxy. A region so barren where the average density of galaxies is so strikingly low that it challenges our understanding of cosmic structure. This is not science fiction, but a very real, very mysterious feature of our universe. Welcome to the Great Void, a cosmic mystery, an abyss of darkness beyond the understanding of the universe and its formation. To truly appreciate the significance of our cosmic journey into the void, we must first travel back in time. Back when the concept of cosmic voids was just a glimpse into the eyes of astronomers. At the end of the 18th century, a new era of astronomy dawned. With the invention of the telescope, astronomers began to map the cosmos with unprecedented accuracy. Yet, as they mapped the shimmering expanse of the Milky Way, they could hardly imagine the vast cosmic structures that lay beyond their field of view. Let's go back to the 20th century. The advent of modern telescopes and observational techniques has opened up the universe like never before. Astronomers realized that our Milky Way is just one of billions of galaxies scattered throughout an unimaginably vast universe. When the distribution of galaxies was plotted, they began to notice something strange. In some areas, there were far fewer galaxies than expected. These areas, originally thought to be observational anomalies, later became known as cosmic voids. Only in the second half of the 20th century did the concept of cosmic voids begin to gain momentum. In the 1970s and 80s, studies of redshifts, the method used to measure the distance to the galaxies, revealed the large-scale structure of the universe. Galaxies were not scattered randomly, but appeared to form a kind of cosmic web with vast expanses of void between them, voids. With the advent of digital technology and more powerful telescopes in the late 20th and early 21st centuries, our understanding of these voids has broadened. Sloan Digital Sky Surveys and 2DF redshift studies have produced detailed three-dimensional maps of the universe revealing the cosmic voids in their entirety. The discovery and exploration of cosmic voids, from the earliest hints of astronomers to today's advanced instruments and methods, represents a fascinating chapter in our quest to understand the universe. Yet, despite our progress, these vast realms of nothingness continue to baffle scientists. The Great Void stands as a separate mystery. At the same time, as we delve into its mysteries, we can't help but wonder, how did it form? As astronomers looked further and more precisely, they discovered an intriguing pattern in the distribution of galaxies. Let's start with the fact that on a large cosmic scale, galaxies are not scattered randomly throughout the universe. Rather, they come together to form complex networks of cosmic structures. These networks, often referred to as the cosmic web, consist of clusters of galaxies, threads connecting these clusters, and vast empty spaces between them. The voids look like vast regions with a much smaller number of galaxies in stark contrast to the dense clusters and threads of the cosmic web. The realization of the large-scale structure of the universe was an important milestone in our understanding of cosmic voids. These voids were not simply the absence of galaxies, but integral parts of the cosmic fabric. Now that we've traversed the cosmic maze leading to the discovery of voids, let us delve into one of the most mysterious voids confirmed to date, a void so large that it's been nicknamed the Great Void. Welcome to the Boötes Void, named after the constellation in which it is located. The Void of Boötes, discovered by astronomer Robert Kirshner and his team in 1981, is one of the largest known voids in the universe. Boötes Void is not only large but also incredibly empty. In an area of space where we normally expect to find 10,000 galaxies, there are only 60 in the Boötes Void. Think of it as a cosmic desert, a vast expanse of emptiness amid a densely populated cosmos filled with galaxies. The presence of such a colossal void contradicts the cosmological principle, which states that when viewed on a large enough scale, the universe should appear approximately the same in all directions. The mysteries of the Boötes Void are not limited to its size and emptiness. For example, some of the galaxies inhabiting the void are bizarrely arranged in a tubular structure, and this feature is not yet fully explained. As we continue our journey through the cosmic seas, our next stop will be another prominent void, which has earned the impressive name supervoid. This is the Eridanus supervoid. The Eridanus superhollow, named after the constellation in which it's observed, is not just a void but a superhollow. It's one of the largest structures ever discovered in the universe. Just to give you an idea of the scale, this superhollow extends about 1 billion light-years across. If you're traveling at the speed of light, it would take you a staggering 1 billion years to cross it from one side to the other. Eridanus supervoid is not only huge but also incredibly barren. Although it's not as devoid of galaxies as the Boötes void, its vast space is still strikingly barren compared to the galaxy-rich cosmos around it. But what makes the Eridanus supervoid particularly intriguing is not just its size or emptiness. This supervoid is related to a mysterious cosmic phenomenon known as the cold spot of relic radiation. A cold spot of relic radiation is an unusually cold region in the cosmic microwave background, the afterglow of the Big Bang. Some scientists speculate that this cold spot could be the result of the Eridanus supervoid. The huge void could cause a phenomenon known as the Sachs-Wolf effect, where photons lose energy as they pass through the void, resulting in a colder patch of relic radiation. As we continue our journey through the cosmic deserts, we encounter yet another mysterious expanse of emptiness. Welcome to the Canes Venatici supervoid. This supervoid, located in the constellation of the Hound Dogs, is a compelling illustration of the scale and vastness of our universe. The Canes Venatici supervoid, like its counterparts, is a region of space with significantly fewer galaxies than expected. To understand the scale of this superhollow, consider this: it's an incredible 1.2 billion light-years in diameter. Like a cosmic desert among the lush forest of galaxies, the Hound Dog supervoid is an area of deep emptiness. While the size and emptiness of the Canes Venatici supervoid are fascinating, the question remains: how did such a massive void form? What process in the early universe could have led to such a vast expanse of void? Although the exact process that led to the formation of voids is still unresolved, several convincing theories have been proposed. The first potential scenario involves the concept of cosmic inflation. It's believed that shortly after the Big Bang, the universe underwent rapid expansion or inflation, which stretched space itself. Quantum fluctuations during this inflationary period may have intensified on a cosmic scale, leading to denser regions and less dense regions of space. Over billions of years, matter gravitated toward denser regions, forming galactic clusters and filaments, and leaving behind less dense regions that became cosmic voids. The second theory has to do with dark energy, a mysterious force that causes the universe to accelerate. Dark energy may have played a role in the formation of voids, pushing galaxies from less dense regions to denser ones, effectively inflating these voids over time. Finally, the formation of cosmic voids may also be related to large-scale structural processes in the universe. As matter in the universe clumps together under its own gravity, forming structures such as galaxies and galaxy clusters, voids naturally form in the remaining spaces. This process is similar to the formation of bubbles in a loaf of bread as it rises and bakes. Just as the dough forms solid structures around air pockets, the universe forms structures of matter around spaces of emptiness. These are just some of the theories scientists are exploring to explain the formation of these cosmic anomalies. But as vast and mysterious as these great voids are, they're just a piece of a complex cosmic puzzle that scientists have yet to piece together. The exact processes that lead to the formation of voids are shrouded in mystery, and uncovering them is a daunting task. One of the main problems is the scale and complexity of the universe. The universe is vast and filled with countless galaxies, each with its own unique properties. Understanding how these galaxies interact and how they affect the larger cosmic structure is a Herculean task. Another difficulty is the elusive nature of dark matter and dark energy. These invisible forces are thought to play a crucial role in shaping cosmic structures and voids, yet our understanding of them is still in its infancy. Without a clear understanding of what dark matter and dark energy actually are, understanding their influence on void formation remains a considerable challenge. Despite these obstacles, current research in this field is dynamic and constantly evolving. Scientists are using increasingly sophisticated tools and techniques, from advanced telescopes to powerful computer simulations, to explore the mysteries of the great empties. Large surveys such as the Sloan Digital Sky Survey display the distribution of galaxies throughout the universe, providing invaluable data for studying cosmic voids. Meanwhile, computer simulations allow us to recreate the evolution of the universe under different conditions, helping to test theories of void formation. In the quest to understand the origin of these vast cosmic voids, each new discovery, each piece of data brings us one step closer to understanding the truth. The great voids have profound implications for cosmology and our understanding of the universe and its structure. They present a unique perspective on the role of dark matter and dark energy, two elusive but dominant components of our universe. Dark matter, although invisible, is the basis of the large-scale structure of the universe. Its gravitational pull helps form the cosmic web of galaxies and voids. The very existence of these vast voids suggests that dark matter played a key role in shaping the universe we observe today. Meanwhile, dark energy, the mysterious force governing the accelerated expansion of the universe, may also play a crucial role in the growth of these voids. By pushing galaxies away from less dense regions, dark energy can inflate these voids on cosmic time scales. But the implications of cosmic voids extend even further. The study of these voids can provide important information that can help refine our current cosmological models and theories. For example, the size and distribution of cosmic voids can be a unique test of cosmological models. If a model can accurately predict the properties of these voids, this confirms its accuracy. Conversely, any discrepancies between model predictions and observations may signal the need to refine or even develop a new theory of physics. In fact, these great cosmic voids, once thought of as mere empty spaces, have taken not the least place in our quest to understand the universe. But what if these voids are more than just empty space? Their study has spawned theories beyond our familiar universe, bordering on the realms of the speculative and the extraordinary. One such theory includes the concept of alternate universes or a multiverse. This is the idea that our universe may not be the only one, but rather one of many universes existing in parallel to each other. According to some theorists, the great empties could potentially be more than just vast spaces of emptiness. In fact, they could be interfaces or gateways to these alternative universes. This assumption is rooted in certain interpretations of quantum mechanics and string theory, which postulate the existence of other dimensions besides the three spatial dimensions and one temporal dimension that we encounter. If these dimensions exist, they could potentially contain many alternative universes, each with its own set of physical laws and properties. In this context, the great empties may be areas where our familiar four-dimensional universe thins and gives way to these other dimensions. It's important to note, however, that this idea is highly speculative. Although it offers intriguing perspective and has inspired countless science fiction stories, it's far from being accepted by the mainstream scientific community. To date, we have no concrete evidence for the existence of alternate universes or other dimensions. Moving on, we encounter the previously mentioned idea, the idea that unites the immensity of the universe with the infinite decimal quantum world. This concept is nothing but quantum fluctuations. In a quantum sphere, particles and energy constantly appear and disappear, creating a frothy sea of fluctuations. But what do these microscopic phenomena have to do with giant cosmic voids? The answer goes back to the earliest stages of the development of the universe, shortly after the Big Bang. During this period, the universe was extremely small and hot. And in such a state, quantum effects could have a significant impact on the cosmic scale. Quantum fluctuations occurring at this time may have intensified as the universe expanded. These amplified quantum fluctuations could lead to an uneven distribution of matter and energy. Regions of lower density could, over billions of years, become the vast cosmic voids we see today. In this scenario, the great voids are like ancient imprints engraved on the fabric of the universe by quantum fluctuations in the earliest moments of its existence. It is important to note, however, that while this theory is intriguing and has some basis in our current understanding of physics, it still remains a hypothesis. Verifying such a theory is a difficult task that requires accurate measurements of the large-scale structure of the universe as well as a deeper understanding of quantum physics and cosmology. Nevertheless, the prospect of connecting the realm of the quantum with the cosmic, the smallest scale with the largest, is tempting. Another fascinating hypothesis plunges us into the complex abstract world of topology, the mathematical study of space and its properties in the context of the universe. Topological anomalies or space defects refer to irregularities in the fabric of spacetime. Just like fabric defects, these defects may represent areas where the normal structure of spacetime is disturbed. But where could these anomalies have come from? To answer this question, we have to go back to the inflationary period of the universe, a fraction of a second after the Big Bang. During this ultra-fast expansion phase, the universe grew exponentially. Although this inflation smoothed the overall distribution of matter and energy, it may also have exaggerated tiny irregularities in the fabric of spacetime, causing topological defects. These defects could then act as places around which matter could not easily accumulate, eventually leading to the vast empty spaces we know as cosmic voids. The study of cosmic voids would not be complete without the study of one of the most mysterious objects in the universe, black holes. Specifically, we're talking about primordial black holes. Unlike the black holes we're familiar with, which form as a result of the collapse of massive stars, primordial black holes are assumed to have formed shortly after the Big Bang. They may have been created by extreme density fluctuations in the early universe. Now, you may wonder, what do these ancient black holes have to do with our great cosmic voids? Well, one claim suggests that these voids may be teeming with primordial black holes. According to this idea, the large voids may be the result of a large number of primordial black holes hiding in these regions. Since they do not emit significant radiation, they would be difficult to detect directly. Their presence, however, would have a gravitational effect, effectively clearing their surroundings and contributing to the enormous voids we observe in the cosmic world. Another theory intertwines the story of the emergence of the great voids with the elusive dark matter. Dark matter, although undetectable by conventional means, is thought to make up about 85% of the universe's matter. It plays a crucial role in the formation of cosmic structures, weaving a vast, entangled network linking galaxies together. These strands of dark matter, known as filaments, serve as supports for the universe, guiding the formation of galaxies and galaxy clusters. But what if something were to break these threads? What if a massive event or unknown force could cause these threads to collapse or disintegrate? That is where cosmic voids come into play. According to this theory, the collapse of strands of dark matter could lead to the formation of these huge voids. The collapse of these filaments would disrupt the flow of matter, leaving behind vast empty expanses. So, as we've already understood, these vast expanses of emptiness are quite far from being barren wastelands. They are a treasure trove of clues and mysteries about the universe and its composition. From the formation of the large-scale structure of the universe to the behavior of dark matter and dark energy, the mystery of the Great Void forces us to rethink our understanding of the cosmos. And while we may not yet have all the answers, every question we ask, every void we explore brings us one step closer to unlocking the mysteries of the cosmos. And remember, every time you look up into the night sky, you see not only stars and galaxies, but also invisible cosmic voids. These silent guardians of the cosmos continue their eternal vigil, keeping the secrets of the universe in their vast expanses.